Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at a different class of compounds, of course, that is heterocyclic compounds. And this is going to have a different way in which we are going to perceive, of course, some of the compounds that we are going to come across, especially in organic synthesis. Now, this class of compounds that are known as heterocyclic compounds are different from the one that we have already discussed in some of our videos, especially for cyclic compounds and aliphatic compounds. So in this case, we're going to look at this different class of organic compounds that, of course, apart from them being or having different chemical characteristics, we're going to also to see that the structural representation for the heterocyclic compounds is a little bit different from the organic ones that we've already discussed. So these compounds are very essential, especially in the pharmaceutical industry and the manufacturing of some of the compounds like dyes that we use in our day-to-day life. So let's try to see and thank you. Welcome. So as I've said, we are going to look at a class of compounds that we call heterocyclic compounds. And as we are going to see that there's a different way in which these heterocyclic compounds appear from the already other organic compounds that we've already discussed, in that their structural representation is different and it encompasses other atoms that we have discussed or we've tried to look at from the periodic table that they prefer covalent bonding other than either losing or accepting electrons. So I'm going to have a small demonstration for the part of a periodic table that is going to assist us in order to determine which are some of the compounds that we refer to as heterocyclic compounds. Now basically this is going to give us an illustration about the concept of course, of bonding and stability that we have already discussed in some of our videos, but we're just going to have a quick recap for this to assist us understand this concept of heterocyclic compounds. So when we were talking about the concept of the octet rule, and this is a rule that is, of course, characteristics with elements or ions whereby they obtain or acquire electrons in their valence shell or lose electrons in the valence shell in order to attain what we call stability. So for stability or for compounds, they naturally tend to acquire the stable states, and naturally tend to acquire the state of stability in a sense that that is what makes them, of course, what we call, or rather makes them maintain their properties or resist change over time. So this octet state from this, the prefix oct means that the valence electrons either attains the number of outer shell after the stability is either 8 electrons by either losing or gaining electrons. So in this case, for those particular set of compounds from the demonstration of a part of the periodic table that I've illustrated, you'll find that most of the organic compounds are formed by this range of elements that appears at this, or rather appears somehow central to this section of the periodic table. In a sense that much of what we have discussed consists of compounds, either maybe the functional groups or the molecular formula of those compounds consist of the much of the elements that have encircled using that red, of course, mark there. So these central elements, in a sense, consider they consider bonding covalently with other elements or similar atoms rather than losing electrons. If we try to see at this extreme part of the periodic table and this one, of course, we find it that at the outermost energy level, these elements gain electrons to attain stability, while this on the other side they lose electrons in order to attain stability. So in an essence, atoms at the extremes of the rows can gain or lose electrons to form an ionic lattice. So in this case, for this, like maybe sodium, it's going to lose an electron to form an ion lattice. So in this case, if it joins with another compound like this other side. So chlorine will gain 1 electron to attain the octet rule, while sodium will lose that 1 electron to attain the octet state. Now for this kind of a compound, it's going to form an ion lattice, which is of course an ionic compound of sodium chloride. So in this case, we're going to see how these compounds prefer either to bond with other compounds covalently to form other ionic compounds. So we're going to see that apart from these atoms making much of the organic compound series that we have already discussed, we saw that for cyclic compounds, for instance, like okay, let me give an example of this is benzoic acid. So suppose I give an example of that one, you see that this kind of an atom appears at the outer part of the ring. There are other cases whereby you find that some of the atoms, either in the middle or here, or maybe as we can extend to this part of the periodic table to encompass phosphorus and sulfur, they form part of the ring of some of the compounds that we're going to encounter in this discussion of heterocyclic compounds. So therefore, the term hetero means that different molecules that are going to form part of the ring of that particular compounds. So basically, that's what we are going to look at and try to see that what is the influence of these particular different molecules in the ring structure. Now, previously we had discussed that this contains only hydrogen and carbon, and in this study we're going to see that the heteroatoms that have been encircled, especially for phosphorus, sulfur, nitrogen, and oxygen, are going to form part of the ring that I've talked about. So I just do away with this. Now we have specific names that we're going to refer to this. So generally when we have compounds, we can either classify them as either carbocyclic or heterocyclic. So this is a broader definition for that. And now for the first one, the carbocyclic, these ones contain carbon chains which are linked together. And that one, of course, these are just as we said from that kind of a denotation, these are cyclic compounds that contain carbon bonds which are joined together. Now for heterocyclic compounds, they contain at least one atom other than carbon in forming part of the ring. Now that is the illustration I've just given. For instance, for a compound that has got 2 carbons and of course oxygen on that particular point, that's one of the examples of compounds that you can refer to as heterocyclic compounds. So by definition, these are compounds that contain at least one atom other than carbon in forming part of the ring. So as we have said, they're cyclic, but instead of them having carbon bonds joined together, they have a different atom, and therefore we call them heterocyclic compounds. Now, as I've used the demonstration using the periodic table that I've drawn on the board, there are different atoms apart from the oxygen that I've illustrated that can be used to form heterocyclic compounds. And this part of the atoms that I've illustrated, which occur at the central part of the periodic table that are then circled with red, of course, and just state them for the nutrition purposes. I said that hydrogen, this is a carbon, nitrogen, oxygen, phosphorus, and sulfur. Now in this case, now that we have been dealing with this, some of these compounds like nitrogen, oxygen, sulfur, and phosphorus, but basically the 3 form parts of what we commonly call to as hetero atoms. that we're going to encounter in some of our illustrations that we're going to talk about. Now, these compounds, of course, hetero compounds can be classified as either aliphatic, so they can either be aliphatic or aromatic, heterocyclic. So as I stated, just like the aliphatic compounds and aromatic series that we have discussed in our videos, these compounds can as well be aliphatic, heterocyclic, which of course have just some basic analogous structures to for aliphatic heterocyclic compounds, just like the amines that we discussed. So these ones are analogous to the amines, the ethers, of course the thiol ethers. Thiol ethers, these are derivatives, of course they contain sulfamides, etc. So in this case, of course, for aliphatic heterocyclic compounds, they are analogous to the amines, ethers, thiols, amides, etc. Now for aromatic, just use this arrow for illustration. For aromatic heterocyclic compounds, then we're going to have compounds such as, of course, I talked about the common name and IU naming system for heterocyclic compounds is unique. We're going to look at that example. But we have a common or just a trivial name for a compound that is known as pyrrole. Fran is part of a cyclic and urethanes. Now these are going to form a part of aromatic compounds, and as we have discussed in one of our videos, the concept of aromaticity states from the fact that these compounds obey the Haeckel's rule, which states that for the system to be aromatic, it has got to be planar, conjugated, and then it has got a 4n plus 2 pi number of electrons. So for these aromatic heterocyclic compounds, they of course consist of this class of compounds, and then number 2, they obey the Haeckel's rule. Now we're going to look at some of the ways in which these organic compounds, these heterocyclic compounds can be named, and try to see how it differs from the ones, the conventional way in which we have been naming aliphatic and other aromatic compounds. So in that case, I'm just going to give it to you an illustration using perhaps a table so that we can be able to understand. Now in this case, just like the alkane series which formed the parent naming system for the other class of organic compounds that we discussed, ranging from the alkenes, alkynes, the carboxylic acid, etc. We are going to see that the nomenclature for the heterocyclic compounds is going to have a specific order in which we are going to do it, in a sense that we are going to consider the hetero atoms that is present. Of course, we have listed it from the demonstration of the periodic table that I've given, and then we're going to see the respective valency for these hetero atoms and their specific prefixes that are going to be attached to this kind of atoms that we are talking about. So in this case, as we can see, for an heteroatom or a compound that contains oxygen of course has a valence of 2, we're going to give it a prefix of oxa. For nitrogen, aza. For sulfur, thea. And then for phosphorus, it's going to be given as phosphor. So for single 3 to 10 member of this series, they are named by combining the appropriate prefix that I've listed on the table with the stem and omitting the letter A where necessary. As you can see, the ending of almost all of these prefixes ends with A. There are some cases that I'm going to give an illustration, maybe using one of the hydrocarbon series, that is the alkanes, and why we need to eliminate either just retain or eliminate the A that is present in these prefixes respectively where necessary. So in this case, I'm going to just give that demonstration before we move ahead, because this is very essential in trying to name the heterocyclic compounds. So I'm going to do that. So I've done 2 tables on the board which are going to assist us in understanding the nomenclature of these heterocyclic compounds in a way that the first table, just maybe try to indicate it using or the table on our left consists of heteroatoms, the valence and the prefix that we have discussed. Now the second table is going to give us a suffix of that specific compound. So in this sense, the ending that is given for these heterocyclic compounds is going to indicate the size of the ring, which is for 3, 4, 5, and 6. And the state of the hydrogenation, of course, that is when we were talking about alkynes, we said that the compounds are unsaturated. Now and then the alkane series formed part of the saturated compounds. Now we're going to see the characteristic ending for this case, of course, is going to create a difference for us to understand. So in the naming of these heterocyclic compounds, we are going to consider the suffixes that have been provided. We're going to get this using, those are just the dashes to indicate that those names are suffixes. So we are going to just have a look at a few examples in order to see which are some of the rules that apply in order to achieve the nomenclature of this specific class of compounds. Now when a compound contains a vowel that come together, as I've said, we're going to drop that or omit one of them in order to form the name. Now I'm going to illustrate that one using an example. For instance, when we were just trying to talk about the nomenclature of alkane series, we said that for a compound like this one, this is a 4-member carbon, so it's therefore comes from the parent name of the butane alkane series, that is butane. So if we are going to name it, of course, if we do the counting for the double bonds, it's going to be 1, 2, 3, 4. So it can be either from side, since the priority for this one can take a priority of that. So counting can be either from the right or left. So therefore we're going to name it as butene. But we have to indicate the position of the double bonds. So in this case, it's going to be named as but. 1, 2, 3. 1, 3. This gives the positions of the double bonds. But there's a condition that we have to meet, in a sense that these double bonds have to be given a prefix di-in. And that one sets a particular condition which we of course need to remove in so far as the IUPAC naming system is concerned, whereby if there is a consecutive order whereby the vowel and another vowel follow one another, we introduce an A here for buta. Remember, this comes from the butane series, so we just retain that A there for the name to be buta-1,3-diene for the IUPAC naming system of this compound. So there are cases whereby we are going to encounter this kind of a scenario, whereby either we need to retain a vowel or a consonant or drop one in order to comply with that specific rule. So that's why that in this statement, it stated that when the name contains a vowel that comes together, vowels that come together or consonant that come together, then we're going to, of course, in this case, because the prefixes and suffixes are made up of vowels, so if the two vowels come together, then we're going to drop the A that comes at that of course these prefixes of the heterocarbons that we've discussed. So we're going to demonstrate that one using an example of that so that we can be able to understand. Now for instance, if we have a compound that is an hetero compound, now that we have understood what it is, like that, now we're going to consider from this kind of a table what kind of a prefix we're going to attach to it. It contains oxygen, therefore it's going to be an oxa for the prefix. And then we're going to look at table 2 for the suffix. First of all, the ring size, of course, it's going to be 3. 1, 2, 3. The ring size is 3, and therefore we are going to use the first row of that. And then the compound is saturated; it does not contain a double bond. Therefore, we are going to consider the second column. This is the first column for fully saturated compound, fully unsaturated, fully saturated. So we are going to consider fully saturated compound column. And then next, it does not contain an N. So if you try to see at this level or the second row, bearing in mind that this is the first for the ring size, this is the first row and the second row. For the second row, with nitrogen or without for the two tables. So if we select the fully saturated compounds, then we are going to consider without nitrogen, and then it's going to give us the salvage for Iran. And there's this last condition that I've discussed, that if the vowels come in that order whereby they're being consecutive, then we are supposed to drop this A in order to get that name. So we are going to have this compound named as oxyren. So the A has disappeared from this. So this is going to be the name of this particular heterocyclic compounds. Let's look at the case scenario 2, where we are going to consider another compound that of course has got nitrogen in its structure like that. So the first thing that we're going to look at, the number of rings for this compound is 3. Of course it's bearing nitrogen, therefore we will use the term as a for the prefix, and then we are going to look for the suffix. It's a 3-member ring. Of course, we're going to look at the first column for this naming of the size of the ring, which is a 3, 1, 2, 3. So therefore, we're going to look at the 3 ring size, and then the prefix is going to be saturated with nitrogen, iridium. So this is iridium, but as we have said, this vowels that comes consecutive will make us drop this A. Therefore, the name will be as iridium. So therefore, this is the format that we're going to use for other compounds. Now, suppose still I can just give another one for 4-member ring, which is containing another heteroatom, or just a heteroatom, that is oxygen. So therefore, we are going to look at this. So first, it contains oxygen, therefore it's going to be an oxa, and then the suffix is going to be saturated, and then it's a 4-member ring size. So we are going to consider this a 10. Vowels following one another, we drop A. Therefore, it's going to be oxa, oxetene. So this is a specific order that we are going to follow. Maybe we can give a last one, as we have talked about saturated, we can just give an example of an unsaturated compound and try to see also how we can be able to name it. So we have this compound which contains nitrogen. Of course, it's saturated, perhaps a aromatic compound. So we just want to look at that. So it's 1, 2, 3, 4, 5. So for one that contains nitrogen, it's going to be aza. The ring size is 5, and therefore it contains nitrogen, and it is of course unsaturated. So we're going to follow this column and look at this. So it's going to be ole. Now if you drop this A that is there for aza, then we're going to have azole as the name of this particular compound. So majority of these heteroatoms, as I mentioned, of course, they use the concept of the common or the trivial naming system, of course, which means the common names that are being used apart from the IUPAC system. Of course, the trivial names are accepted for some of these compounds, and this one can be referred to as pyrrole. So this name compound can be referred to as pyrrole. So we're going to see different compounds. Maybe if it's pyrrole is mentioned somewhere, then we can be in a position to mention. So in this case, there is a scenario whereby you can find that these two different atoms have appeared in one specific structure, and there's going to be an order of preference for this, whereby oxygen is going to take preference over sulfur and over nitrogen. So in case they appear, then we're going to pick these suffixes and prefixes in that, specifically the prefixes in that order. Now, for instance, for a compound that contains oxygen and nitrogen, we're going to follow this order of preference and find that for oxygen it's oxa, and then for nitrogen it's going to be aza. Therefore we're going to remove this, it is axa. Now for the prefix for that one will just appear as that one. So therefore this is also the similar order that we're going to use for other compounds. For instance, for the compound that contains just a minute. For a compound that contains, for instance, sulfur and nitrogen. So sulfur and nitrogen, sulfur we have said is here. Let me just put it this way. Okay, for a compound that contains sulfur and nitrogen, sulfur we have said, so sulfur will take preference over nitrogen, and sulfur is going to be here. And then for nitrogen it's going to be aza. So we are going to drop this A, it will be the aza, etc. So in that case, that is the order in which we are going to follow to name compounds, heteroatoms that contain more than one compound in its one heteroatom in its structure. Maybe we can give a specific example of a compound like this that contains nitrogen and oxygen in its structure, and try to see how we can be able to name it. So we said that in order of preference, oxygen is going to take preference, so therefore we're going to give it axa, and then the nitrogen is going to follow, of course, which is going to be aza. So therefore we are just going to have a prefix that is made up of zaza. But in this case, for the suffix, this is a 1, 2, 3 member ring with, of course, with this is this is saturated with nitrogen. So therefore, we're just going to consider nitrogen since it's the one that's being given a condition here. So aza, iridine. In this second case, still we're going to drop this A so that we can have oxa, pyridine. So this is going to be the name of the compound that is formed by those specific heteroatoms. Now these heteroatoms are very important, as I mentioned from the start, that they are very great medicinal value, so far as maybe the industrial use are concerned. And they are very flexible in a sense that modification can be done so far as solubility is concerned, or maybe one can alter their solubility, polarity, and even lipophilicity that we are going to discuss about later. This is also lipophilicity. This is to do, we are going to mention some of these terms maybe in proteins and carbohydrates, but for that case, they can be able to be manipulated to come up with other compounds which are of essential or biological importance, essential use or biological importance in that case. So that is it for today, guys. Thank you for listening to our discussion. I hope that this concept of heterocyclic compounds has been understood insofar as nomenclature is concerned. And whenever we're going to mention pyrrole or acetylene, then we can be able to understand what it pertains to. So thank you for today. That is it. Bye. God bless.